Hi everyone. Hopefully you've all noticed that there's no homework due this Friday, and that's to encourage you to just work on Project 2. So we're done with all the talk we're going to do about the theory of asymptotic analysis, and for pretty much the rest of the semester we're going to learn data structures. You guys have already learned a few really simple data structures, arrays and linked lists. Today's going to be the first data structure of some complexity that we're going to learn. First of all, I'll teach you the general idea of what we're trying to do, something called a dictionary. And then I'll talk about a data structure called a hash table that's designed to give us this capability. So to introduce dictionaries, let's suppose that we want to create a computer-based dictionary. But to keep things simple to start with, we're going to restrict ourselves to two-letter words in English. So there's a dictionary where we have a bunch of two-letter words, and we know their definitions. And so just like with a paper dictionary, it's pretty easy to look up a word and find its definition. We'd like a computer to be able to look up a word and find its definition as quickly as possible. Now, there's an official name for the word. The word is called a key that addresses the definition. So key is the official hoity-toity computer science word for this. We're going to use, of course, this structure for more than just looking up words. We're going to use it to do any kind of map, any kind of sort of function from one discrete set of objects to another can be implemented as a dictionary. But going back to two-letter words for now, there are 26 times 26, which is 676, different possible two-letter words if you just consider every combination of letters that you could put together. Not all of them are actual English words, but we'll have a much simpler data structure and much easier lookup if we just assume that we have room to store a definition for every one of those words, and then if some of those words aren't actual words, then that's okay. We just never look them up. So given that, to implement a dictionary, we're going to use an array of 676 references. And then we can just use that array to map every word to a dictionary meaning. So to insert a definition into the dictionary, here's what we're going to do. We're going to define a function called hash code. And what hash code does is that it maps each possible two-letter word or more generally, maps each possible key to a unique integer in the range 0 to 675. And then we use that integer to just look up the word in the array. And we make that particular entry in the array, we call that the bucket, where we're going to store the definition for that word. And then whenever we want to look up that definition, we can look it up basically in constant time. So let me show you some code that does this in the simplest way possible. That's better. Okay, so I have a class of words And the total number of possible words is 26 times 26. There's 26 letters in the alphabet, and these are two-letter words. And here's my function hash code that I talked about. And the way you actually implement it is you take advantage of the handy fact that Java lets you treat a character as a number. And so you can mix characters with ints. So you take whatever the first character is in the word, and you subtract a, and that gives you a number between 0 and 25. Like a would be 0 and z would be 25. And then you do the same thing with the second character, giving you another number between 0 and 25, and those signify your letters. And you multiply the first one by 26, and then add the second letter. And so that's how you map a two-letter word to a unique number between 0 and 675. Now, here's our dictionary class. The way our dictionary works is we just create a table right from the start with room for every possible word that you can get by snapping two letters together. And whenever I want to insert a new word along with its definition, I just find the right place to store that word, and then I store the definition in that entry of the table. And whenever I want to find the definition of a word, well, I just pass in the word, I look in the same place I stored the definition, and I return it. So very, very simple. Any questions so far? Yeah. Yeah, so each of these operations, insert and find, are constant time. So these are all big O of 1 operations here. And that's what's nice about them is, you can look things up super fast. The problem with this is that we're storing two-letter words. And you'd really like to have a dictionary that stores the whole English language. And I think the longest word in English is Pneuma ultramicroscopic silicovolcanoconiosis, which is 45 letters long. So you would need to be able to have an array of length, 26 to the 45th, to use this technique to store every word in the English language. And this is one of those magic numbers that is bigger than the number of estimated subatomic particles in the universe. So you're not going to do that. We need to be a little bit more clever if we want to store the whole English language in a dictionary. And so that's where hash tables come in. Now, what I desire to do with hash tables is to support three operations: the insert operation, the find operation I just showed you, and it's also nice to have a remove operation so I can take something out of the dictionary if the meaning of a word changes or I need to revise or update the definition. So I want to do these three things. I want to be able to do them with arbitrarily large words, so I need something more clever. So let's proceed one step at a time. First of all, I'm going to use little n to denote the number of keys that we're actually storing in the table. Now, this is not the maximum possible number of words. This is not this 26 to the 45th number here, because we can't deal with that. Instead, this is the actual number of words we want to store. Now, the English language, even if you go to the Oxford English Dictionary and pull up every obscure word ever used in the 1500s, is still less than 1 million words. So n for the English language is, I think, somewhere around 700,000. So this is something that a computer can cope with. And we're going to let capital N be the number of buckets we use to store these keys. And the number of buckets is not going to be 26 to the 45th either, because we can't do that. We'll never have enough memory. But what we're going to do is we're going to make n, big N, a bit larger than n, say. It's roughly about the same size as n, maybe 20% bigger. It doesn't really matter, as long as it's in that range. So n is big N, the number of buckets, is a bit bigger than the number of things we want to store, but it's way, way smaller than the possible number of keys we could store. So what we got to do now is compress all these things so that we can store them in a much smaller table than 26 to the 45th power. So what a hash table does is it maps a huge set of possible keys by possible keys, I mean every possible permutation of letters. So lots of possible keys are not English words. But there's this huge imaginary set of possible keys, but we're only going to use a few of them in practice. And so what we're going to do is we're going to map those into a much smaller number of buckets, capital N buckets, by applying something called a compression function to each hash code. So the idea is that if I want, I can still map every possible English word to a number in the range from 0 to 26 to the 45th power minus 1. I can calculate that number. But then I have to compress it down so that I'm not using more than a few million buckets. And, well, there's lots of ways you could do a compression function. Here's the most obvious and simple one. So just by taking the hash code and going, I'm going to take that mod n, where n is the number of buckets. Now I have a number between 0 and n minus 1. And so everything fits in my table now. By the way, just a reminder, hash codes are often negative, especially the way they're implemented in Java, for instance. So don't assume the hash code is always positive, and therefore don't assume that the mod operation is the same as the % sign in Java. So hopefully you guys learned in Project 1 that if you want to implement the mod operation, it's kind of like %, but you have to do a little extra something if the input number is negative. So remember that when you implement a hash table, which you will this semester. And the only problem with this scheme is that there's a lot of words, and there's enough buckets to fit them in. There's probably more buckets than words, usually. But this mod n is kind of just a random way of compressing a really big space of words into a small number of buckets. And because it's kind of random, you're likely to have collisions. And a collision is the circumstance where several keys hash to the same bucket. Which, for instance, well, this happens if the compressed version of one hash code is equal to the compressed version of some other object's hash code. And so we're going to spend most of this lecture, and part of the next, figuring out, well, how to deal with collisions, how to reduce the likelihood of their happening, et cetera, et cetera. Any questions so far? Yes, sir. This is H here. So H is just the name of my compression function. You make my H's really tall. Or was that what you were referring to, or something else? Okay. Other questions? Yeah, sir. How is the hash code determined? Well, that's a black art, and we're going to talk about it a little bit today and mostly next lecture. But for the words that we've got right now, what I can do is I can take a word, I can think of each letter. There are 26 letters in the English alphabet, or the Roman alphabet. And so you treat each of those as a digit between 0 and 25, and you pretend the word is a base 26 number. And then you just express it as a number and compute it, convert it into the internal binary format of the computer, and then, which hopefully your TA taught you how to do that during the very first week's discussion section, and go from there. Other questions? Yeah, yeah. Mm-hmm. Yeah. So big N is the number of buckets. And so the references to those buckets will just be a number between 0 and n minus 1. No, big N is the number of buckets. Little n is the number of keys we want to store in the dictionary. Well, you should choose big N to be close to little n. That's how they're related. You get to pick big N. The application gets to pick little n. So here's how we handle these collisions. We do something called chaining. What is chaining? Each bucket is no longer going to store just one word and one definition. Instead, now each bucket is going to store a linked list of entries. And that linked list is called a chain. So if several keys are mapped to the same bucket, then those definitions all reside in the linked list for that one bucket. And so you can put as many definitions into one bucket as you need to. But chaining creates a second problem. Now that we're storing multiple definitions in one bucket, if I want to look up a word, how do I know which of the definitions stored in that bucket corresponds to my word? And the answer to that is, well, when I store these chains, I have to store not just the definitions, I have to store the original words as well, so I can make sure that I'm getting the right definition out of the chain. So whenever I store a definition in the table, I'm going to store the key with the definition as a pair in that table. And now I'm going to have a chain of entries, and each entry is defined to be a pair. An ordered pair consisting of a key and some value that's associated with that key. And this will be our general terms that we use for dictionaries and hash tables. In this particular case, the key is an English word, and the value is the definition of that word. So now let me draw what this actually looks like. So I've got def table is going to be my table, and it is a reference to an array. And this array might go on for a good long time, but I'll... And within each bucket, there might be one item stored. One entry, which consists of a word and its definition. Or there might be several stored in one. Or you can have buckets that just by chance didn't get anything mapped to them at all and just contain a null pointer. And so this goes on. And so on and so forth. So I'm sort of using an abbreviated representation here. So when you see this, what this really is it's an object that has a key pointer and a value pointer and a next pointer, which in this case is null. That's what that node is. So expand all of these nodes appropriately. Each of these is actually 3 different objects, and the node itself contains 3 fields. Any questions about that? So I told you that there are some operations I want to support. So let's look at how we can do those operations. The function prototypes I write up here, I'm going to be following Goodrich and Tomassia. So this is the way they define their insert method, and so I'm sticking with that. What the insert method does is it takes a key and a value, it combines them together into an entry object, and it stores that entry in the hash table. And for some reason, it also returns the entry object that it creates to store your key and your value. I don't know why, but it's there if it's convenient for you. So here's how we implement this. First of all, you compute the key's hash code. So in the case of an English word, that might mean treating it as if it were a base 26 number and converting it into the computer's internal number format. Then compress it so it fits in the table, and that tells you what bucket to store it in. Then you insert the entry. And when I say entry, please remember that I mean the key and the value together into the table, or specifically into the chain for that particular bucket. So into that linked list it goes. Once you've inserted a few things into your dictionary, you might want to look something up. So there's a find operation. You pass it a key. You don't know the definition, but what you get back is an entry which includes both the key and the associated value. So now you have the definition. And that's how you look up the definition of a word. And so the way this works is pretty similar to the way you insert. Once again, you hash the key, which means finds its hash code, and then compress it. And that tells you what bucket it's in. Then you have to search through that linked list. So we search through the chain for an entry. with the specified key. And if you find an entry that has the right key, you return it. But if you get to the end of the chain and you haven't found any entry that has your word in it, then your word's not in the dictionary, so you just return something that says your word's not in the dictionary. So Goodrich and Tomassia, they just return null. And the last operation we want to support is removing a key. So again, okay, so remove is going to do everything find does, plus it's going to remove the key, the whole entry from the dictionary. And when I say it does everything find does, it even returns the entry after removing it from the dictionary. So it basically works almost exactly the same way that find does. You hash the key, you search the chain, and one extra step, you remove it from the list if it's found. And then you return the same thing that find would return. Now, there's one extra little issue here, which is, what if you try to insert multiple copies of the same key into the dictionary? Like maybe a word has two different definitions, and you want to put each of those definitions in as a separate entry. How does the hash table handle it? Well, when you design a hash table, you actually have a choice. So if you have two entries with the same key, then there are two approaches that are commonly taken. And the first one is the one that Goodrich and Tomassia have implemented in their book, which is insert both. So now your chain has two different entries in it that have the same key, or 5 different entries, or 100 different entries. And then if you do a find operation on that key, you just return one of them arbitrarily. Whichever one happens to be first in the chain will probably do. And in fact, Goodrich and Tomassia also provide a find all operation, which, if you want, will allow you to enumerate all of the items matching a certain key in the hash table. So if you want all of them, they give you a way to do that. The second approach you could take is replacement. So the second approach is, I'm going to say there's only allowed to be one entry with a given key in the dictionary. And if you try to insert a new one with the same key, I'm going to overwrite the old one. And so you might ask, which approach is best? And the answer is it totally depends on what your application needs. Some applications need number one, some applications need number two. You have to understand your application. So any questions on any of these operations? All right. Onward then. So I'm going to give you a big warning, which is once you've inserted something into a hash table, sometimes you insert an object into a hash table, and you still have references to those objects from somewhere else. Like maybe there's some variable in your program that has a reference to the object that you just inserted into a hash table. For instance, your hash table might be a game board in a game of chess or network or tic-tac-toe or something like that. And you can insert a game board into a hash table, and there are reasons why you would want to, which I'll talk about next lecture. If you do that, you should not change the object once it's inside the hash table. Or at least you should not make a change to the object that will change its hash code. Because if you change an object in a way that changes its hash code, it's now in the wrong bucket, and you'll never be able to look it up again and find it. And that kind of warning actually applies to just about every data structure we'll study in this class, is that sometimes once you've stored something inside a data structure, changing that something can be dangerous. So next I want to talk about the performance of hash tables. And it's actually a complicated subject, and we'll only be able to talk about parts of it today and other parts later in the semester. But really, one of the big things that the running time of a hash table depends on is how much stuff you try to pack into how big a hash table. And so people usually talk about hash table's performance in terms of the load factor. The load factor of a hash table is little n over big N. Remember, little n is the number of keys we're storing in the hash table, and big N is the number of buckets we have to store them in. Now, we want the load factor to stay small. Somewhere around a small constant like 0.8 would be nice. Or even 1.2 wouldn't be bad, but if the load factor stays low, meaning close to a small constant, and if the hash code and the compression function are good, and we'll talk more later about what it means for those to be good, and if there are no duplicate keys, because after all, duplicate keys all wind up in the same bucket, then the linked lists stay short. Like the chains are, 1 or 2 or 3 or 4 items apiece. And therefore, each operation takes constant time. Let's just say order 1. But what it comes down to is that the running time of any hash table operation depends on how big the chain is that you have to search through. And so if the chains grow long, it's not going to take big O of 1 time anymore. In other words, if the load factor gets really large, and by really large, I mean that little n is way, way bigger than big N by a huge margin, then, or little n keeps growing, the number of items keeps growing, but the size of the hash table isn't growing, it's staying the same, then these chains are going to get as long as, well, on average, little n over big N. And so in the limit, as little n keeps getting bigger and bigger, this is going to run in linear time, which is very slow. Well, let's say theta n time. I mean, in the limit, as little n goes to infinity and big N doesn't grow, your worst case running time is going to be at least proportional to n. Now, having multiple buckets still helps because it divides the running time by about big N. So if big N is 10, it only takes 1/10 as much time to find an item, maybe. So the point is, you don't want to let the load factor get big. You want to try to keep big N the same size as little n, roughly speaking. To really do a proper analysis of the running time of hash tables based on this requires some probability theory. So we're going to put that off till the end of the semester, but we will come back and do a proper analysis. Any questions about that? Yeah. What is the disadvantage of choosing a really huge big N? That's a good question. Actually, the only possible disadvantage is, well, the startup cost, because it does take big N time just to create the table in the first place. So if N is a billion, that might matter. The other thing is that it just takes up a lot of memory, and you might want to use that memory for something else in your computer. But, by and large, if you aren't going to have more than 100 items and you just pick big N to be 10,000, that's probably not going to hurt your performance at all. In fact, so choosing big N to be 10,000 makes a lot of sense in that case. Other questions? Okay. One of my assumptions up there is that the hash code and the compression function are good. So I'm going to start talking today about what good hash codes and compression functions are, and I will continue that discussion on Friday. So you'll recall that, again, that the way this works is you have a key. It gets mapped to a hash code. And that gets mapped to a number between 0 and n minus 1 by the compression function. Now, designing these things well, the hash codes and the compression function, is a black art. It's a black art. And so what I will try to get across is examples of why certain things don't work. But to some degree, it's hard to really explain why the things that do work, do work. The things that work because nobody has found any flaws in them yet. So let's talk about what the ideal is first. Here's what we ideally like to accomplish. We would just like to have a magic function that maps every key to a random bucket. With each bucket being equally likely. Why not order them? Well, the idea is that you want to have as few collisions as possible. And if you map each key to a random bucket, that's pretty much going to give you as few collisions as you can get. Unless, well, in practice, there's very few data sets that you have to work with that have some special structure where you can improve on a random mapping. I mean the two different keys, two different keys, two different words, say. Suppose the words tin and rock both go through this process, and they both wind up mapping into bucket 3. Then that's a collision. Yeah. We don't like collisions because they cost us time. They slow down the search operation in a chain. They slow down the remove operation in a chain. Well, they slow down all the operations on a hash table. Yes? Mm-hmm. So, like, pick. So what you're saying is you'd like to have a function that just maps every possible item to a different bucket, or every. Okay. The fact is nobody knows how to do that. So, I mean, that's really the bottom line, is that if you just drop a bunch of keys on my head and say, come up with some fast-to-compute function that will map each of these keys to a different bucket, nobody knows how to do that. In fact, now, we do know how to, if you give me a bunch of keys, I do know how to write a computer program that will map each of those keys to a different bucket so that each bucket is different. And this data structure that allows me to do that is called a hash table. So, but I can't use a hash table to compute the hash code for another hash table because that just slows things down. Now, so the reason people use random function is because that's the best anyone's come up with. No one knows how to break that, do better than that. Yeah. Sorry, what is in... So, the bottom line is, what is the total running time? And the total running time is something I'll show you how to analyze late in the semester. But it comes down to the total running time has to do with the number of collisions, but it also has to do with the lengths of chains. So if a chain grows really, really long, and you do lots of operations that access that particular chain, then that's what really costs you. So the cost of doing lots of operations on a hash table is roughly proportional to the square of the length of the chains that you're dealing with. So you don't want to let the chains grow long, and that means you don't want to have too many collisions. Now, this ideal, when I say map each key to a random bucket, I do not mean that every time you look up the key, like the word tin, you roll the dice and you get a different bucket each time. No, for a hash table to work, a certain word, a certain key, has to always map to the same bucket. So I don't mean random in that sense. But what I mean is it's random in the sense that you roll the dice once for any given word. So tin maps to bucket 3, but then you have a fast function that can compute, that can hash tin and get 3 over and over again every time. That's what you really want. But it's actually pretty tricky or difficult in practice to achieve this ideal, to create a function that's totally random and maps every different word to a completely random bucket. That's actually hard to do. So what we usually do in practice is look for functions that approximate that. So the hash code is the harder part. So let me start with the compression function, which is the easier part. Now, problem is with both hash codes and compression functions, it's easy to mess up and create a hash code or a compression function that causes far more collisions than are really necessary. Just to give you an example of a bad compression function, an idea of what to look out for, what can go wrong. Consider this example. First of all, suppose the keys are integers. More specifically, suppose the keys are ints, type int, and suppose that each integer's hash code is just itself. Which is pretty good because at least the hash code isn't going to cause any collisions. But now what about the compression function? Suppose the compression function H maps the hash code to hash code mod n. And suppose that n is 10,000 buckets. I decide, I think I need a table big enough to store 8,000 to 10,000 items, so I'll use 10,000 buckets. Okay, what's wrong with this? Well, the thing that's wrong with this is a lot of applications don't generate all integers with equally likelihood. You know, it's not random, but it's systematic. And so maybe one application, just for whatever reason, all of the integers are divisible by 4. And that the only keys it ever needs to hash are ones that are divisible by 4. Well, if you take a number that's divisible by 4 and then take it modulo 10,000, it's still divisible by 4. That's very bad news because it means 3/4 of our buckets are wasted. They're never being used at all. So we thought we had a hash table of size 10,000, but really we have a hash table of size 2,500. And we're not doing nearly as well as we thought we should be for the amount of memory we're using. And we have at least 4 times as many collisions as necessary, and therefore we have about 4 times as much running time for each operation, walking through the chains, trying to find things. Any questions about that example? Yeah. No, right now. What's that? Next lecture? Well, chaining is how we store keys in the same bucket. The problem that we're facing now is how to reduce the number of collisions. And here, in this particular example, you fix it by making big N prime. So it seems like magic, but choosing big N to be prime, the number of buckets, now means that if you're getting keys that are consistently divisible by some number, after you take the modulo big N, they won't be divisible by any particular number anymore. So you just want N to be a big prime, and that tends to solve this problem. Now, for reasons I won't discuss, but If you want to see the reasons why, read section 9.2.4 of Goodrich and Tomassia. This compression function is even better. A times hash code plus B. Then you take it modulo some large prime. And then you take it modulo the number of buckets in your table, which should be much smaller than P. So again, A, B, and P are positive integers. P is a large prime. And P should be significantly larger than the number of buckets that you want to use. And so, I mean, a lot of you won't understand this till you take 61C, but you can think of this mod P operation as scrambling the bits really well. And then the mod N operation makes it fit in your table. And, well, one of the obvious advantages of this over that is that now the size of your table doesn't have to be prime. Any questions about that? Okay, more on hash tables on Friday, including good hash codes.